Hi, welcome back to Autonomous Mobile Robots. My name is Paul Fergale, and I'll be your teacher for this exercise on wheeled locomotion. So in this exercise, we're going to use the mathematical tools that we learned in this topic to derive the equations of motion for a very common robot design, and that's the differential drive robot. So let's start by looking at the configuration of this robot. So this again is a top view schematic of a differential drive robot. So these rounded rectangles here are the wheels as seen from the top. And it has these two fixed standard wheels aligned along this common axis. And what we want to do in this worked exercise is to stack the wheel equations for this configuration. It also has this spherical wheel here, but we're just going to ignore that as a passive contact point to stabilize the robot. So to give some notation here, the turning of the right wheel is phi dot r, the turning of the left wheel is phi dot l. We assume both wheels have the same radius r, and the distance between the robot coordinate frame, that's this one here in the center, and the wheel's contact point is B, and we assume that that's the same for both wheels, so this is also B. Okay. Now, recall from a previous segment that we derived these two constraints for a standard wheel. So we have the rolling constraint and the no sliding constraint. Just to review the notation again, we have this beta is the steering angle, alpha is the angle of the steering coordinate frame, L is the distance from the robot coordinate frame to the center of the wheel. And actually, I'm going to simplify these equations by taking this r theta xi dot I and just say that that now will be the velocity of the robot expressed in the robot coordinate frame, just to make it easier. Now for this particular robot configuration and this wheel diagram, we can just write down what those configuration parameters are, alpha, beta, and L. So for the right wheel, we have alpha is negative pi over 2, beta is 0, and L is B. For the left wheel, alpha is negative pi over 2, beta is 0, and L is negative B. And if you plug these numbers into these equations and stack them up, you end up with these stacked equations, one for the rolling constraints and one for the no sliding constraints. And that's just a really straightforward substitution and then evaluating those cos and sine values. Here I've actually left the B, the baseline of the robot, and the R, the wheel radius, as symbolic constants, and we'll just propagate those through the equations so you sort of derive the general equation for any differential drive robot. So here on the left are the stacked matrices again, and recall that we call those for the rolling constraints J and for the no sliding constraints C. Now the first thing we want to do is look at this C matrix to derive the degree of maneuverability for this particular robot configuration. So recall that's a sum of the degree of steerability and the degree of mobility. So the degree of steerability, in this case, we have no steerable wheels, so that's just 0. For the degree of mobility, we've defined that delta M to be 3 minus the rank of C1. So if we look at C1, clearly it has just one independent column, and so the rank is 1. So the degree of mobility is 2. And finally, the degree of maneuverability is just the sum of these two terms, and so of course that's 2. So we'll now go back to these matrices. So we have the stacked rolling constraints and the stacked no sliding constraints. And actually, if we stack those two together, we get the stacked equations of motion. And just to make it simpler to manipulate these equations, I'm going to give these names. So this left-hand side matrix I'm going to call A. This right-hand side matrix I'll call B. And then the stacked wheel velocities will just be phi dot. And so you end up with this A xi dot r equals B phi dot. And if we want to solve for the differential kinematics equations, we have to manipulate these equations to solve for either xi dot or phi dot. But if you look at those matrices are not square, so we can't do a standard inverse. So what we do actually is we use the pseudo-inverse. So first we'll do the forward kinematic solution. To solve for xi dot r, we're just going to do this A transpose A inverse, A transpose B phi dot. So I'll start by writing down what we know. So this row here will be my row for intermediate results. So we know what the form of the A matrix is. We know what the form of the B matrix is. And the first part of this equation is just this A transpose A. So I just put those two matrices here, A transpose and A, and do the matrix multiplication. And you end up with this nice, simple diagonal matrix, which has 2, 2, and 2b squared along the diagonal. So I'll just put that in my row of intermediate results. The next part of the equation is this A transpose B. And so if I put those matrices right next to each other, again, this is a really simple matrix multiplication. I end up with this R and BR, and then R and negative BR. And I'll put that again in my row of intermediate results. The next thing is to do this A transpose A inverse. And because this is a diagonal matrix, it's really simple to do the inverse. So I just take 1 over the element on each diagonal. So 1/2, and 1 over 2b squared. Next, I'll just put next to that this A transpose B. So that's this matrix here from above. And I do that matrix multiplication. It's again quite simple. And I end up with this R over 2, R over 2b in the first column, and R over 2, negative R over 2b in the second column. And that's actually the forward kinematic solution. But, you know, all we've done up to this point is just apply some basic matrix manipulations to come up with this. But if you look at this, it actually has really, really nice intuitive interpretation. So the forward velocity, so this forward velocity in the robot frame is just the sum of the average of the speeds of the two wheels. So here I've done, you know, phi dot r and phi dot l averaged, which makes intuitive sense. Next, the no sliding constraint is satisfied. So because the robot y-axis is lined up with the no sliding constraint, you can see that this is essentially 0. So whatever wheel speeds we put in, we will never get side slip. And finally, you can see that the angular velocity just comes from the difference in the speeds of the two wheels. And you can see this is also nice and intuitive. So angular velocity, I think, is in this direction. So if the left wheel speed is larger than the right wheel speed, then you get negative angular velocity. So this is sort of like theta dot is less than 0. But if the right wheel speed is greater than the left wheel speed, then you get theta dot is greater than 0. So again, you have this nice interpretation. Oh, furthermore, you have the baseline here. So the farther apart these wheels are, the less the difference in wheel speeds affect the angular velocity. We can continue this by looking at the inverse kinematic solution. So the last time we solved for xi dot, this time we're going to solve for phi dot, and you essentially use the same pseudo-inverse solution here. So again, I'll start with what we know, A and B. I'll compute B transpose B, which is a really simple multiplication where you just get R squared along the diagonal. I'll put that in my intermediate results. Next is B transpose A, which is again another simple matrix multiplication where you just get R, and then in the first column, and then BR, negative BR in the third column. I'll take the B transpose B inverse, which again, because this is a diagonal matrix, I can just do 1 over the components on the diagonal. Multiply that with B transpose A, and you end up with, again, a simple matrix. 1 over R in the first column, and B over R, negative B over R in the third column. And that is essentially our inverse kinematic solution. And again, this has a nice intuitive form. So for both wheels, some part of the rotation of the wheels is explained by motion in the robot's x direction. And the other part is explained by the angular velocity of the robot. And as the angular velocity gets bigger, the right wheel speed gets faster. So that's again this. So this is theta dot is greater than 0. And as the angular velocity gets big, the left wheel speed gets smaller. So again, simple matrix manipulations, but a nice intuitive result. So as a summary, we went through this worked example of a differential drive robot. We see that the degree of maneuverability is 2, and we derive both the forward differential kinematics equations and the inverse differential kinematics equations. So, thank you for your attention.